All right, so let's see if I can manage this. I managed to land the coveted post-lunch spot here. So you guys are either really hungry or really tired because you just ate, I guess. Or hopefully you're here because you have a disk array and you'd like it to be faster, or you're just lost. I can relate to you on any of those levels incidentally, except for the tired because I haven't eaten yet. So I am Paul Tuckfield. I am a DBA for a long time. I'm now a manager of lots of architects and DBAs and stuff at YouTube. I was the first DBA at YouTube, first DBA at PayPal, and I sort of run with a crowd of people who build a lot of websites. And so I was lucky enough to get a lot of experience as a DBA doing the thing that you seem to always come down to in crunch time, which is tuning I/O. And that's why I'm here today. I thought I'd see if I could see if I could pass something along. How many people actually have some sort of I/O problem today? Yeah? A couple. How many people have multiple disk arrays? If you got just one disk, or if your database fits in memory, just go eat. It's fine. You don't need to listen to this. If you have an I/O problem, or you just need high I/O, maybe it's not a problem. Yeah, you got it under control. You probably went out and bought a multiple disk array. So I think the brand names I know of out there, are EMC and Hitachi. I've worked with those before. Most of the people here probably do not, but you probably work with things like Mega RAID, freeware, yeah, by hands. And then the other ones I'm familiar with are Adaptec and what was the other one? LSI Mega RAID, right? So I think that's pretty popular. So it looks like maybe freeware and Adaptec are relatively popular, and so there's probably other ones out there too. Hopefully I'll give you some generic stuff. These are the ways to make I/O faster. First of all, don't do I/O. Everybody knows that, right? That's why everybody caches. That's what Memcache is about. That's what big, fat caches are about. If you don't do an I/O, you'll never have an I/O problem. Also, and then, these are sort of like database 101. If you do I/O, you would want to do just a few I/Os to get just the rows that you want, and that's more or less saying, indexing. That's another very simple thing that people learn. The very first thing, I didn't even have an index on my table. If you must do lots of I/O, you should do it sequentially. That's one thing that's really not obvious to. It's a little counterintuitive. It's a little bit of a Zen thing there. But I am talking about OLTP today, and this sequential sort of strategy is probably something that does not apply to OLTP. But if you are going to do something like a data warehouse application, counterintuitively, you probably don't want to use indexes. You want to use this ripping fast sequential I/O and do lots of them in parallel. And lastly, one of the things I suspect is happening to a lot of people with MySQL databases and sort of commodity controllers is that when you buy a controller that has 10 disks, and you want to do a lot of I/O, what you want is all 10 of those disks to be busy at the same time. You don't want 10 I/Os to come to that array and then have them somehow go in there one at a time, or access one drive at a time. You want all those red lights going at the same time. And surprisingly, the reality is that even me, I found myself, wait a minute, only one disk at a time is going on this array that I just bought. You may pay a lot of money, or you really need that thing to go faster, and you're surprised because something is tripping you up. So you have to make sure that you're really doing multiple concurrent I/Os. I wrote, my slides are kind of messy. I kind of threw them together, but and so I think I already talked about this. If you're going to do a lot of I/O, you want to do it sequentially. But another counterintuitive thing here is what that kind of means is read ahead. If you're going to do a lot of I/O, there's times when you want to do read ahead. That's almost never true in OLTP. Read ahead is almost always counterproductive because at a minimum, it does a bunch of I/Os that you don't need typically because you wanted to get that one row and it went ahead and read a million rows out in front that you're never going to read. Or at worst, it just flushed a bunch of the caches, violating rule 0, ruining your caches. So again, for these, four great commandments or whatever here, don't do any I/O. That means tune your queries first. So if you're doing a lot of I/O and you're trying to tune your I/O well, go back and just make sure that you really need to do that I/O, obviously. Do as few as possible. That means indexes in OLTP, and we won't be talking much about sequentially except to say make sure that the file system and the controller aren't doing it for you. trying to help you by doing it when they're really just going to screw you up. And then lastly, you got to be able to look at the IOs and understand at a little bit deeper level than just percent busy is 100% on my disk array. Well, sure, you're 100% busy, but are you like 8 union guys in the shop and 1 guy's doing work, or are all 80 of you guys coming away, because you've all got stock. So unions get a bad rap. That's a crappy joke. I'm from Detroit. Anyways, so.
Can you go back? You had a little digression there that I missed.
Oh yeah, flash drives. Yeah, I had a little, like we were talking the other day, I showed up here like 2 days ago thinking that, I didn't even look at a counter. I said, I'm gonna go see the Percona stuff. Showed up, doors locked. Oh, these guys show up checking out the room. Hey, it's not for 2 days. And then we started talking and said, oh, okay, well, I'll do a talk. But I just having these little anxiety attacks of like, well shit, all my mojo is all about, making these disk drives work and, there's flash drives. What fun is that? But I think most of these rules still apply. 0, 1. I think 0 and 1 are certainly still going to apply. The sequential versus random is the main thing that's just going to get thrown out the window, and that's one kind of big mojo that you can have as a DBA. But then this concurrency issue on number 3 probably will still apply. I mean, unless they, the Linux kernel and everything gets mature enough, maybe a little more like you can kind of say that Solaris and some other ones kind of have, evolved to default where they did not sort of have these crazy stupid defaults that caused serialization for you. So flash drives, it's a little creepy for me because this is there goes some of my mojo, but yeah, we'll see. It'll be interesting. I'm actually evaluating some flash drives now, but they are pricey. There's still all the price trade-offs and everything, and there'll probably be. I believe that there's still just the domain of problems that you need to care about this stuff will get. I don't know if it gets smaller or bigger because it's going to be gigantic data sets, ever larger data sets, but most of the world will care less and less about it because a couple $1,000, they've already got 1 million cores, they got tons of RAM, and now they're going to have perfect disk drives too. So most OLTPOs won't care. But anyways, these are my generic rules. Never cache anything below the DB. That means you don't want it to cache in the file system. You don't want it to cache in the RAID controller. Those are just, they're at best a waste, and at worst they actually hurt you. There's one exception to that. You probably want to cache writes to the RAID controller. If you can turn off read caching, you probably want to do it. You want to leave write caching on. And that's of course a battery-backed array where if it goes into RAM but the system crashes, you won't lose your data. Or you don't care if you lose your data. And that will help your performance. So that's the one place other than the database that you should cache the data is on writes to the controller. Another thing is never do read ahead anywhere but in the database because it's a little bit similar to that first rule. I'll try to explain this a little bit more later, but it's a sort of a corollary to don't cache anything because read ahead is just like a sort of a caching heuristic. You're caching more than you really should. Another weird thing is always make sure that the chunk size, and the stripe size too, I guess, of the array that you're setting up is much, much larger than your block size because every I/O that you do, you want it to engage exactly one spindle, not multiple spindles. What you want is all those spindles, if you've got 10 spindles, you want 10 spindles servicing 10 different read requests. And then lastly, make sure you are actually doing those concurrent I/Os, and what that means is understanding I/O stat, roughly speaking. I got some fancy graphics here in an attempt to explain all this. What should be true of your system is that my fancy depictions of cache here are mostly trying to show you that it should be true that the database cache is much larger than the file system cache, which is much larger than the RAID cache. It's usually true. Sometimes you're in a weird situation where you have, I suppose you have a ton of RAID cache, but that means you spent a lot of money. It's more expensive on the RAID cache. You could have spent less money and got more memory in the database. And the top cache is the best cache. It's the closest to your query, and so you want data to be in that cache. But the weird thing here is that you want to give most of that memory on the box to the database cache, which means that the file system has less cache. There's all sorts of interactions that can happen there too, which are very usually undesirable, unpredictable, and undesirable. But again, the main thing here is that they get smaller and smaller and smaller, which is the opposite of what an L1, L2, L3 cache is going to be in a CPU setup, right? The L1 cache is super fast, but it's of necessity small. The only reason they have an L2 cache is because they can make it way bigger than the L1 cache. Here it's backwards, right? And what it means is that the memory that you gave, or accidentally gave, or implicitly gave to the file system cache is essentially a waste at best. Because should have gave it to the database cache. Why? I tried to make a little example here where they read blocks 0 through 11, and this is what the LRU caches look like now. You know, the RAID cache is only small, so it only has 10 and 11 in it, right? The file system cache is a little bit bigger, so it's got 7 through 11 in it. And the database cache, of course, I hope you made it the largest, has got even more stuff in there. Well, suppose you want to read block 2, right? Well, you missed the DB cache because block 2 isn't in there. It's sure as hell not in the file system cache because it's smaller. It's sure as hell not in the RAID cache because that's even smaller. So you read it from the disk and you put it in all 3 of those caches, and then you got block 2 to satisfy the query. Well, you know, somebody comes back and reads block 2 again, they're going to get it out of the database cache. And even though you put it in those other caches, they're never going to fall through because the database cache is bigger. So, you know, so that should illustrate hopefully pretty clearly that it's just a waste. I threw a lot of text in here because I made the mistake in some talks in the past of either not sending out my slides or not having enough in here. So if these wind up on a website, hopefully they'll explain something to somebody who can hear me, my wonderful rhetoric here, or whatever you call it. So the corollary there, you know, hopefully it's reasonably easy to see from the same example that now. I didn't make any very good graphics for read ahead, but my graphics were crappy to begin with. Read ahead is the same thing. If you go and read ahead a bunch of blocks, even if you what you'll wind up doing is evicting pages from the cache that have probably have a better chance of being hit than the pages that you've read ahead. The read ahead usually only applies when you're doing full table scans, and you sometimes want to do full table scans out of necessity to do some big aggregation. It can be fast, you know, in a data warehouse kind of environment. But OLTP, forget it. You never want to do it. You never want to do read ahead. And some controllers and things will try to do it for you to attempt to help you. You want to turn it off. And if it's happening in the file system, if it's happening in the RAID controller, you want to turn it off. Here's where I'm trying to explain why you would still want to cache writes in the RAID controller. So I've attempted to make a fancy illustration here of how you start out with that cache I showed you before, and 10 and 11 all turned red. Why? Because you modified 10 and 11. Now they're dirty pages, and dirty pages. And NODB had to flush them to the file system. The file system flushed them to the RAID controller. And in a battery-backed RAID controller, I guess at that moment, you know, in the nice, you know, sub-millisecond amount of time, the RAID controller is going to tell everybody, yep, everything's okay, got it. It's committed to my memory. I got it up here. And so when a read comes along, you've done a burst of writes. And the memory allows you to just burst those writes in a very short amount of time. And you sort of now have a debt to pay in terms of I/O. Those dirty blocks in that RAID cache must eventually be retired to the green disks down there, which will take much, much longer than sub-millisecond, right? There's 2 blocks. If I take, you know, 5, anywhere from 3 to 10 milliseconds each, you know, it's a 20 or 100-fold longer. So it borrowed some bandwidth there. But now when a read comes along, it's got to wait for, the cache has been filled up with writes. It's got to wait for one of these red blocks to be evicted, then it can do a read and satisfy the query. And so the bottom line here is that this ability to tell you right away in 1 millisecond, yes, your IO's done, don't worry about it. It's not really existed, you know, don't worry about it, I got it in memory. That's a very good thing, but when the RAID cache must be shared by reads and writes, you're going to get this kind of serialization where reads will sometimes have to wait for writes to be evicted. And so I tend to think of that as, so what you really want is for the writes to be written to this, buffer really, to the RAID cache. And then your reads to just bypass all of those later. No file system cache, and don't go through the RAID cache, just send it straight to the kernel.
very adapted to the web market, but I found one case when it's not, when it's the opposite. For example, in a big bank where I used to work, they have more than 2,000 database instances. So then they put this fabulous RAID system with 256 read read cache on their side, and it's just a question of having no memory at all in the database system.
Right. So, so the observation made here is that there are cases where a large RAID cache is very helpful. I think my counterpoint to that is I believe you, it's true, but there's you know what a sort of self-starting, scrappy startup would say is that, and you know, me as a consultant, I would never say that to the bank because I would much rather charge them money, or sell them a very large array. But what's true there is if you have, so what he's saying is that there's 1,000 hosts, they're all attached on a SAN to this array. The array has an immense cache. And so each of these thousands of database instances all get very good cache hit rates, and they are probably on machines that have very small amount of memory. Might apply to like a system aggregator or something. But what I'm telling you though is that is because that array is undersubscribed, right? Each one of those hosts can only use a tiny fraction. And if a few of those hosts get hot or do something, they will destroy performance to the detriment of all the other hosts, right? They will burst to the cache of that one large shared array. They will fill it up with these red blocks, and then some other poor sap on instance 997 will try to just do a simple read, but he can't because the array has allowed this giant burst of writes to happen, and can't service that read because it's caching reads. First of all, why do it? And second of all, it must wait for these writes to be retired. So there are times it is true that read cache is not 100% evil, but my contention is that you should have more memory on the host because it's cheaper, and therefore the lower read caches are useless because they're smaller, and therefore you should just not even cache reads and cache writes. There are times when you're going to get a silver bullet. You're going to buy a big fat array, and whatever rig you've got set up, you're going to put it in there, and it's going to solve your problems, and it's worth the money. You know what I mean? But setting out, trying to reduce costs, trying to really scale far, and/or trying to stay in the commodity world, yeah, it's going to turn that upside down. And again, I got lots of words there for somebody who might read this online. And so I try to think of burst writes as borrowing bandwidth, right? They're sending it to cache in the array, and they must be retired later. So I've harped on that long enough. This is why you don't want to have a small chunk size. It's slightly counterintuitive. You're thinking, hey, I got an OLTP system. I want to get a block. I want that block to come back as fast as possible. So I want all the disks spinning. Give me that one block. So this is what it would look like is if you were trying to read a 16K InnoDB block and you use a 2K chunk size, that's what would happen. It would seek on all those drives, and all those drives would send you, 1/8 of your block. That's bad because in an OLTP environment, what you typically want is multiple requests to be in parallel. If you issue 3 requests, what's it going to have to do? It's going to have to seek all the drives, give you block number 1. Then it's going to have to seek all the drives again, give you block number 2, seek all the drives again, give you block number 3. So it all adds up to 3 times the seek time. Whereas if you had a large chunk size, when you asked for these 3 IOs and you gave them all to the disk array, you would say that IO is on disk 1, this other, or 0, the other IO is on disk 2, and the other IO is on disk 7. They would each seek concurrently, get your block and send the blocks back. Technically, they're not literally concurrent, but you might as well think of it as concurrently sent back to the host because there's so much more bandwidth on the PCI bus than there is in the disk array. So those 3 IOs all fly back to you concurrently, and they only take 1 times the seek time of the drive. So this is presumably the answers to how you get all this. How do you never cache anything below the DB? It more or less boils down to ODirect. If you can't turn off the file system cache, look into the VM swappiness parameter, because when the file system starts caching a lot of stuff, it starts paging other stuff out that you want to keep in, including InnoDB itself. So the swappiness parameter can help you sort of prevent the file system cache from growing too much to the detriment and paging crap out. There are some issues with ODirect that I think might be the reason why people have so much problems with it, and I think they are in the kernel or whatever, but I did find a workaround for these, which I'll try to get to.
What kind of file system do you use?
And it's an excellent point. I have tried a few different file systems, but there are some file systems, people have told me that, you know, if you tried like XFS or some other file system, you might not see this issue. But the issue that I'm talking about here is when I want my files, when I want, you know, multiple IOs to be issued to the controller, they're serializing somewhere between NODB and the driver. And that's observable in IOStat, which I hope to be able to get to before time runs out. But it may be true that sort of...
Definitely a problem on X3 or what?
EXT3, yeah, and also Riser, and I tried EXT2.3 and Riser. But since I found a workaround, I didn't want
API states that you should not import a single outstanding drive to a file, and that is usually implemented above the file system.
Yes.
The DFS suite or something.
Right. There are points where you can serialize in the file system because it doesn't know whether it's going to do an extending write. It has to lock the entire, it has to lock the global file system structure. And these are well known to Oracle DBAs and people who work on Solaris, right? Because these problems were solved like 10 years ago. The generic rule for cache writes only in the RAID control. This is what I did for AdaptTech. Worked really well. It implements more or less my ideal of only doing writes to the cache and not doing reads. And it also does not do read ahead. Thank you very much. This is what I did for Mega RAID. Didn't get nearly as much experience on Mega RAID as I did on AdaptTech. We sort of settled on AdaptTech, and now we have hundreds of them. These are sort of conflicting here. It doesn't really get to the ideal I want. I'm not positive what Direct IO is doing there. I think you're okay with write back in normal and not doing Direct IO and letting it do some read caching in the controller. But I think that controller might be a little bit smart about not allowing too many writes to burst to the controller. I got 1 minute left. The freeware didn't do much. I didn't get a lot of chances to try any of this, but I couldn't see any way to shut these things off in the freeware. The most important thing to understand is how to tell when your IOs are actually going in parallel. This is an attempt I made to explain what service time versus percent busy. You could look at your array and say it's 80% busy and say, oh, I don't have any bandwidth left on my array. But what you have to understand is that if those Ds on the side are individual disk spindles and these little blocks represent the histogram of the time it takes to do IOs on these blocks, both of these arrays are roughly at 80% busy, but one of them is doing 9 IOs in that time period and the other one's doing only 4. It's a factor of 2, and you probably can get even more than this. Why? Because that one is concurrent. What you have to do is understand how to figure that out when looking at IOStat. And that is how I detected this problem that I had. I don't know if it's exactly what the problem was, but that's how I knew there was serialization in the array, in the kernel layer. That's how I went out and fixed it. And that's, here's some real world examples. And the way I fixed it, I don't know what it was, but instead of striping everything in the array and presenting a single drive to Linux and then putting a file system on it, we presented mirrored pairs to Linux, thereby getting the benefit of caching and back cache, and then use MD to stripe it. For whatever reason, that convinced the file system and disk controller layers to issue concurrent writes as measured by stat. If you can remember that formula, that's how you'll know.
Did you try IO schedulers?
Yeah, we tried a couple different ones. Deadline. To be honest, I'm not sure which one we're using right now.
My experience is that no scheduler is best if you have big write.
It looked like it to me. But what we did is when we settled on this, what I did is by observing what I was getting in terms of IO performance in IOStat, I was satisfied that the kernel and the file system were pushing IOs down to the array sufficiently. But yeah, it looked to me like don't do anything, no ops, just get the hell out of the way and let the database issue. Also, there are times when NODB might not be issuing as many IOs as it could. You can also tell that in IOStat.